Evening, everyone. I can't hear you. Good evening, everyone. Um, wish to welcome you once again to today's evening service. And for our special presentation this evening, it is my singular honor and privilege to welcome Mr. Matengele Kaira, who's going to be presenting on artificial intelligence. Just a brief background about our speaker. He's currently a manager in charge of information systems at Mopani Copper Mines with work of experience of over 13 years in information systems. He holds a BSc in computer science as well as a master's in computer science. He is passionate about data and technology, as well as emerging trends and themes such as information technology, which is significantly disrupting our way of life today. He is a personal friend of mine and a personal friend of many, as well as a family man, and he loves his God. So allow me to welcome Mr. Matengele once again this evening. What do we say to welcome him?
Good evening, everyone. As introduced by the previous speaker, my name is Matengele Kaira, and I'm here today to talk to you about artificial intelligence. What is artificial intelligence? Most of us think of the Terminator and iRobot when we hear this term. Even though this is becoming a reality, there is much more to it than this. Artificial intelligence, simply defined, refers to the ability of a digital computer or computer-controlled robot or device to perform tasks commonly associated with intelligent beings. In other words, artificial intelligence is about computers mimicking human intelligence. These tasks that can be performed include, but are not limited to, autonomous vehicles, which most of us know as self-driving cars, artificial generative intelligence, predictive analytics, usually used in business forecasting, and facial recognition as well as object detection. What are the main techniques used in AI, artificial intelligence abbreviated as AI? The first is rule-based systems. These are very simple systems that are condition-based. They rely on a particular path being taken if a certain condition is true, or a different path being taken if the condition is false. So these are simple systems which either do A if a condition is true, or B if it's false. The second technique used is state space search. This is an algorithmic approach that uses clever strategies to search a state space. This is very useful for situations where there are many possible states and you're looking for a clever way to determine which would be the best states. An example of this would be in a game of chess, at any given stage, what are the most likely moves and which one is the best. This approach, however, can be processor intensive for large state spaces. Unlike rule-based systems, both state space search and rule-based systems don't have the ability to learn. The third technique used is that of machine learning. Machine learning is unique in that it learns from past data instead of following explicit predefined rules. This is similar to how human beings learn from their experiences. This type of model is capable of learning from past mistakes and adjusting and improving its performance. It does, however, require very large data sets, similar to those generated by social media. And that is the reason you find most social media platforms today are free to help collect this sort of data. So what is this machine learning? Machine learning is a subfield of artificial intelligence that uses algorithms that are trained on data sets to create self-learning models that are capable of predicting outcomes and classifying information without human intervention. This involves feeding large volumes of data, usually labeled data, into a model. So it can attempt to find a pattern or identify a pattern between the data that's fed in, which is the input. This input are usually the things we know. And the output, label, this is the thing that we're trying to predict. There is often also a threshold percent that is determined, that is used to determine acceptable results. This threshold can vary on a case-by-case basis. In certain cases, it might be 70% accuracy. Other cases, it might be 90% accuracy. But generally, we expect this threshold to at least be more than 50% of accuracy. In other words, the model must be correct at least half the time. Now, this machine learning that we've talked about, what are the main techniques that are used in machine learning? There are two main techniques used to build and train models in machine learning. The first technique, which is out of scope for this presentation, but I will still touch on, is statistics. So as most of you know, in mathematics, statistics can be used and applied to a data set to try and make a prediction of what will most likely happen. Equally, in computing, statistics can be applied to make predictions with reasonable accuracy. The second technique that is normally used is something known as neural networks. These neural networks are what will be the focus of today's presentation. So what are these neural networks? A neural network is a digital representation of the functionality of the human brain. In other words, it attempts to mimic the human brain. This network is usually made up of several layers of neurons. And these layers are normally represented as a network of perceptrons. There's a small diagram there on the screen, for those who can see it, that shows an input simplified simply as ones and zeros, a stage called do stuff, which is the inner workings of a model, and an output phase that mimics some kind of useful information or output generated by a model. So what types of problems can these neural networks solve? The first type of problem is classification problems. These are problems where you've got discrete groups or categories of something, and you've got new data that you're trying to determine which of these classes does it fall in. A simple example could be a system that reads data from a video camera feed and tries to determine unsafe situations and notifies someone once one of those is present. The other type of problems that are solved by these models are regression problems. These are more the typical problems that most people are used to. So these are problems where the rate of change of input and the rate of change of the output is consistent. So there is some relationship between the input data and the output data, and a change in the input data normally results in a similar change in the output. The other types of problems that can be solved with these algorithms are clustering problems. There are times where an individual or an organization has a set of data, but they do not know what categories exist in this data. Neural networks or machine learning can be used to automatically classify this data into groups based on the characteristics of the data. The fourth type of scenario is associations. This is commonly used by most online stores and other businesses. You notice, for those that have done some form of online shopping, that when you buy an item, shortly after, you're given a suggestion for similar items that you might be interested in. And a lot of the times you find the items that are suggested actually are things you're interested in. Behind the scenes, there are association algorithms at play. Another simple example that you can relate with in everyday life is things like most of our music players of our streaming services today. If you pick a song and play a single song and hit next, normally you'll notice that the app will keep playing songs that you find interesting despite you only pick the first song. That also is an example of an association algorithm at play. So how does this neural network work? So the building block of a neural network is something known as a perceptron. This perceptron was first implemented in 1957 by a gentleman known as Frank Rosenblatt. This initial implementation was a hardware implementation. So the circuits that were mimicking this neural network were hardware-based circuits. These networks at the time were single-layered. What that meant is they could only deal with one type of input. So because of that, they weren't very popular because they could only solve simple linear problems. As a result of this, over the next 20 years, from the late 1950s till about 1980, this technology was mostly sidelined and there wasn't too much development in that space. In 1980, however, multi-layer networks brought about the ability to solve more complex and non-linear problems. This obviously was necessitated or was possible because by then software development was now a thing, and these circuits or these networks could be implemented in software and not just hardware, making it possible to have a different layer of a network dealing with every stage of the input. A simple example, just to put this into context, would be in 1957, the network, for example, if you needed it to predict the cost of a house, would do so simply by using the size of the square area covered by the property. But in the 1980s, however, more inputs could be used to determine the value of this property. For example, the neighborhood it's located in, proximity to other essential services, and things like that. In the 1990s, we saw the early stages of deep learning, or what is known as deep machine learning. And this was an important phase in the advancement of artificial intelligence and machine learning. To put it into context, on your screen is a diagram of a simple perceptron or a simple neuron. This is, you see on the left, you've got some inputs represented by X, running from X0 to X2. Now, this doesn't mean that this neural network can only take 3 input. You could have hundreds of inputs on that line there, but this is just a simple illustration. Along the arcs, you notice there are some letters labeled as W0, W1, and so forth. These are the weights. The weights signify the importance of each of those inputs in determining the outcome that is required. For example, if someone was looking at properties to purchase, some of the inputs would be proximity to shopping centers like malls, proximity to good schools, safety of the neighborhood, proximity to one's parents, and so forth. You notice that depending on the person, the weights of importance of each of these inputs will vary. Some people might find it critical to be near a good school, whereas others might find it more important to be closer to certain services like malls and the like. You'll notice further down in that network, there's a summation symbol. That summation symbol represents a weighted average or a weighted sum in this case. So the simple computation performed here is the input value is multiplied by the weight along the arc. The resulting weighted sum is the result. But this weighted sum does not always make sense to the consumer of this model or to the person using this neural network. Hence, there is something extra known as an activation function. So this activation function is simply something that gets the weighted sum and converts it into something that makes more sense to the consumer or to the person using this network. In this example, you can see the activation function used is a step activation function. The output of this simple perceptron is simply a true or a false. Meaning, if the weighted sum produced a value above 0.5, the step function would evaluate that as true. If it produced a value below 0.5, the weighted function would evaluate that as false. So how do these neural networks learn? So a neural network learns by utilizing what is known as training data. So we pass labeled data, and the network compares its prediction with the label. So what we do initially is, you've got a set of data, you split it into 2 sets. Your first set is your training set. Your second set is your testing set. So initially, when the model is untrained, you give it the input, and you also give it the label, which is the expected prediction. The computer attempts to make a prediction, and because you've told it what the expected output is, once it's done, it compares its prediction with the label of what it was supposed to be. If this prediction is wrong, it returns, adjusts the weights, and tries again, each time getting closer to the correct prediction. So after a few hundred runs or a few thousand runs, usually you end up with a model that is quite accurate. Once you feel you now have an accurate model and are ready to put this model to the test, you pass your testing data. But this time, you only give the model the labels after it has made its predictions. So this time you give it the input, the model makes its predictions, and you compare its predictions with the labels that you already have. Because this is historical data. You already know what happened. During this testing phase, if the accuracy of the model is found to be fit for purpose, meaning the prediction accuracy exceeds the threshold that is set, then the model has passed and can move on to the next stage and be pushed into production. This exercise of trying to predict, getting it wrong, routing back again to try again, is known as back propagation. One thing worth mentioning is the perceptron diagram that I showed earlier is a simple representation of a neural network. In reality, you've got millions of those perceptrons in a network. So that's what these hidden layers on the screen there represent. The diagram on the screen there is showing a model that has been given data or pictures of an elephant. And then someone takes photos of parts of an elephant and feeds it into the model. The hidden layers, which is the various neural networks, process that information and attempt to make a prediction. If the output is found to be incorrect, then it tries again, and each time adjusting the weights. So what is this back propagation? So back propagation is the iterative process by which a neural network uses a feedback loop that involves sending back errors in its prediction for the model to try again. Each iteration makes the neural network adjust its weights. And this in turn improves the prediction accuracy. This process is repeated over and over until an acceptable threshold for error is reached. This is the reason why most neural network models, when being built, require a very large amount of compute or processing power because of this iterative process. So the calculation of these losses or these variances between the predicted output and the label, which is the expected output, usually utilize mathematical concepts such as calculus, which are out of the scope of this presentation.